The difference of two cubes identity says that for all real numbers x and y, x cubed minus y cubed equals x minus y times x squared plus xy plus y squared. So this identity allows us to factorize a cubic expression into the product of a linear term and a quadratic term. The sum of two cubes identity says that for all real numbers x and y, x cubed plus y cubed equals x plus y times x squared minus xy plus y squared. So this identity similarly allows us to factorize a cubic expression into the product of a linear term and a quadratic term. And as we will see, the sum of two cubes identity can be derived from the difference of two cubes identity. So in some sense, they are the same thing. They are equivalent. We can verify the difference of two cubes identity for specific values of x and y by substitution. So if x is 10 and y is 5, then x cubed minus y cubed becomes 1000 minus 125, which is 875. That's the left-hand side. The right-hand side is x minus y times x squared plus xy plus y squared, which becomes 10 minus 5 times 100 plus 50 plus 25, which is also 875. If x is 10 and y is minus 5, then x cubed minus y cubed becomes 100 plus 125, which is 1125. That's the left-hand side. The right-hand side, which is x minus y times x squared plus xy plus y squared, becomes 10 plus 5 times 100 minus 50 plus 25, which also turns out to be 1125. And it's interesting to note that the expression 10 plus 5 times 100 minus 50 plus 25 is exactly what we would get if we were to substitute x equals 10, y equals 5 into the expansion for x cubed plus y cubed, which is x plus y times x squared minus xy plus y squared, as you can verify. And we will see exactly why that is the case later on. This is the first algebraic proof of the difference of two cubes identity. We show that the right-hand side can be rewritten in the same form as the left-hand side. So we have x times x squared is x cubed, x times xy is plus x squared y, x times y squared is plus xy squared, minus y times x squared is minus x squared y, minus y times xy is minus xy squared, minus y times y squared is minus y cubed. And we see that plus x squared y cancels with minus x squared y, and plus xy squared cancels with minus xy squared to leave us x cubed minus y cubed as required. This is the second algebraic proof of the difference of two cubes identity. We show that the left-hand side can be rewritten in the same form as the right-hand side. So we have x cubed minus y cubed equals x cubed plus 0 minus y cubed, which equals x cubed minus x squared y plus x squared y minus y cubed, where we've rewritten 0 as minus x squared y plus x squared y. Now we factorize the first two and the last two terms to give us x squared into x minus y plus y into x squared minus y squared, and we can factorize the second term using the difference of two squares identity to give us x squared into x minus y plus y into x minus y times x plus y. And now we factorize out the common term x minus y to give us x minus y into x squared plus y into x plus y. And this expands into x minus y times x squared plus xy plus y squared as required. We'll now prove the sum of two cubes identity, and in fact we'll derive it from the difference of two cubes identity. We saw earlier that 10 cubed minus 5 cubed can be expanded as 10 minus 5 times 10 squared plus 10 times 5 plus 5 squared, and 10 cubed plus 5 cubed can be expanded as 10 plus 5 times 10 squared minus 10 times 5 plus 5 squared. Now these look very similar, and in fact they differ only by a few sign changes. So here we have a negative sign, here we have a positive sign, here we have a negative sign, here we have a positive sign, here we have a positive sign, here we have a negative sign. And the reason for these sign changes can be explained by the fact that minus x all cubed equals minus x cubed, as you can see if you expand it like so. Now, since minus x all cubed equals minus x cubed, we can multiply both sides by minus 1 to give us x cubed equals minus of minus x all cubed. And we shall use this identity to prove the sum of two cubes identity. First note, however, that if x cubed equals minus of minus x all cubed, then x is what we call a dummy variable. The name of the variable is irrelevant, so we can equally well write y cubed equals minus of minus y all cubed, which is the exact form that we are going to use in our proof. Now, we want to factorize x cubed plus y cubed, which is the sum of two cubes, but we note that we can use this identity to turn x cubed plus y cubed into the difference of two cubes, which we already know how to factorize. And we do that by replacing plus y cubed with minus of minus y all cubed. We now use the difference of two cubes identity to factorize this expression as x minus minus y times x squared plus x times minus y plus minus y all squared. And that simplifies into x plus y, because minus y is plus y, times x squared minus xy, because plus x times minus y is minus xy, plus y squared, because minus y squared is plus y squared. And we're done. So we can now see that the sum of two cubes identity is simply a variant of the difference of two cubes identity. For example, if we wish, we could expand 10 cubed plus 5 cubed as 10 cubed minus minus 5 all cubed, and then use the difference of two cubes identity. And of course, the reason that we can do that is due to this fact that we demonstrated earlier. This is a geometric proof of the difference of two cubes identity. So first recall that an expression like a times b times c represents the volume of a cuboid whose sides are a, b, and c. So the expression x cubed minus y cubed, which is the difference of two cubes, represents the volume of the shape shown below. It's a larger cube x cubed with a smaller cubed y cubed removed from one corner. So the volume V of this shape is x cubed minus y cubed. At least that's one expression for the volume of this shape. We can find another expression for the volume of this shape by considering these component parts, which we can shade here in green. We have this cuboid here, and we have a smaller cuboid here, and we have the largest cuboid, which is this part. And the sum of these three volumes must add up to V. In other words, the sum of these three volumes must equal x cubed minus y cubed. I've called these three volumes V1, V2, and V3. And for V1, we can see that the cuboid has sides x, y, and x minus y. So v1 equals x times y times x minus y. v2 has sides y, y, x minus y, so v2 equals y squared times x minus y, and v3 has sides x, x, x minus y, so v3 equals x squared times x minus y. Now v, which equals x cubed minus y cubed, can also be written as the sum of the three smaller volumes, which we can write as v3 plus v1 plus v2, which equals x squared into x minus y plus xy into x minus y plus y squared into x minus y. And we can now factorize out the common term x minus y to give us x minus y into x squared plus xy plus y squared, which we can now see is equal to x cubed minus y cubed as required.